Hello everyone, let's take a look at our next problem. Find the equations of the tangent plane and the normal line to the given surface at the specified point. Z equals 3x squared minus y squared plus 2x, and the point is 1, negative 2, 1. Okay, so we have a surface parametrized by x and y. How does this tangent plane and normal vector thing work? So one thing that comes to mind, we should be able to find the normal vector by thinking of the surface as a level set of a function of three variables, x, y, and z, right? Let me write down what the surface is first. So this is the surface, or we can think of the z as a function of x and y, and the point we're given is 1, negative 2, and 1. I suppose we should check quickly that this point does in fact lie on the surface. 3 minus 4 plus 2 is equal to 1. Okay. So I think the way that I think about doing this is we're going to define the function f x, y, z to be equal to 3x squared minus y squared plus 2x minus z. And then the surface corresponds to the set of points where f of x, y, z is equal to 0. And if we put a different constant here, that's going to give us, in some sense, like a shift of the surface. And so the normal vector to this surface is going to be given by the gradient of this function evaluated at this value of x, y, and z. So let's take a gradient of this really quickly. The derivative with respect to x is 6x plus 2. The gradient with respect to y is negative 2y, and the gradient with respect to z is negative 1. So we have to evaluate this at p. And what does this give us? 8, 4, negative 1. So this is the normal vector at this point. And if we have, the normal vector to the surface, there's also a way of parameterizing pretty easily the linear equation which defines the tangent plane. So we're asked for an equation of the normal line. So an equation for the normal line, I'll write this as L of t is equal to the point P, 1, negative 2, 1, plus a parameter t times 8, 4, negative 1, where t is any real number. So that'll give us a line through this point with this direction vector. And then the plane, how do we do this again? So if I let x, y, z represent an arbitrary point on the plane, then x, y, z minus p and I take a dot product with this normal vector, that should be equal to 0, right? This is basically just saying that if I draw any vector in the plane emanating from P, right? So this is a vector which comes out of the point P onto any other point in the plane. That has to be perpendicular to the normal vector of the plane. So we've got x minus 1 times 8 plus 4 times y plus 2 minus 1 times z minus 1 is equal to 0. And if we distribute things here, we have 8x minus 8 plus 4y plus 8 minus z plus 1 is equal to 0. And grouping everything, 8x plus 4y minus z plus 1 equals 0. So there's the equation for the plane, which is tangent at the point P, and there's an equation for the line, which is normal to the surface at the point P. Can check really quickly that the original point P does in fact lie in this line. We have 8 minus 8 minus 1 plus 1, and that does equal 0. Okay. Yeah, a lot of this, I didn't necessarily remember exactly what all these formulas are, but understanding, the biggest thing to understand here was that if you have level sets of some function, which in 3 dimensions, that's going to give you a surface, the gradient of that function is going to point in a direction which is perpendicular or normal to the surface at any given point. And then it's just a question of translating that into an equation of a line. And then to find the plane, once you have the normal vector to a plane, just sort of imagining the geometry of, taking a vector which lies in the plane, of which there are an infinite number, parameterized by something like this. The dot product of any vector in the plane with the normal vector has to be equal to 0. And that's exactly going to give you the equation of a plane if you just write that out and expand it. So nice little sort of calculus and geometry problem. If I have any other comments or find some mistakes, I'll write them in the description. Thanks for watching.